All right, welcome back, everyone. Our next speaker is Gregory Kozyreff. So it's a pleasure to welcome Gregory to the INI. He'll give a talk on Stokes' phenomenon in the propagation of weakly nonlinear wave packets. Thank you very much.
Good morning, everybody. First of all, I would like to congratulate Philip Thrin and Chris Howells for organizing this very timely workshop, and also to thank them for giving me the opportunity to contribute. In my opinion, one of the most pleasant things to teach to students is wave packets, because they have like the perfect mix of simplicity and complexity, and you can use them as a unified description of a whole array of things in nature. And so to fix the notation, I'll call the fast carrier envelope in this way, with beta the wave number, and it's modulated by a slow amplitude. And what's very nice and useful with them is that obviously here the fast oscillation has a phase velocity given by this formula, and then you have this group velocity, which is the velocity at which the information or the modulation translates over time. And so they are related by this simple function, the dispersion relation. And I think it gives a sense of power, both to the teacher and to the students, when they realize that with this simple formula you can describe so many things in nature. And I would like to just review with you 3 examples that are, for me, rather striking and important. First one is propagation of light pulses in optical fibers or waveguides. It can be photonic ships. And here, obviously, timing is very important with these pulses to arrive at the right place at the right moment. And the reason why I want to mention this thing is that in optical fibers, you can go along very long propagation distances so that nonlinear effects have time to settle in. And despite the presence of nonlinearity, the formula for the group velocity is still valid. I also like very much this example here of the wake of a boat, where here again you can use the concept of group velocity to derive the width of the cone here, which is 39 degrees more or less. And if you attach a frame to the boat like this, x plays something like the role of time. And so you have a 2D space, and you have the same kind of exponential as here, and you can use a dispersion relation between the two. You get a group velocity for the flow waves, and that gives you this 39 degree. It's really great to see that independently of the boat speed, of the boat size, and even on the strength of gravity, as long as gravity and inertia drive the motion, this gives you this 39 degree angle. And then, well, as a student, I was particularly impressed by this. If you look at an electron wave packet in a perfect crystal, you know that you can label the wave function by the wave number k, and then the energy or frequency of the wave function is given by the sinusoidal shape. And if then you subject this electron wave packet to a uniform electric field, this electric field will give momentum to the electron, and that has the effect of increasing k linearly with time. And as a result, from the formula of the group velocity, it's the slope of this curve here, sometimes the group velocity is positive, and at other time it's negative, so that there is no net motion under the influence of electric field. And that's quite amazing that in a perfect crystal, you put an electric field and it produces no net current. And so you need actually some impurities for the electron wave packet to collide and to be randomized, so to speak, so have to have a net current. Okay, these examples are just 3 out of a myriad of other examples, and from this you can deduce that the formula for the group velocity is very useful, it's universal, it's robust, it's always true. And therefore, I was quite pleased to find out that there are some circumstances where the group velocity, the formula for the group velocity, doesn't properly describe the speed of a wave packet. Okay? And when does that happen? So this is my wave packet. You need to let it propagate for a sufficiently long distance to be described by the nonlinear Schrodinger equation, so that you have weak nonlinearity that settles in. And then you also need to work in the vicinity of a frequency such that both the group and phase velocity are close together. So don't panic. The formula for the group velocity mostly remain valid. It's only in an exponentially small velocity, vicinity of this working point that thing changes. So why did I expect things to happen differently than the usually expected law in this situation? It's because I had a previous experience on localized pattern where you also have 2 scales. You have a wavelength and a slow amplitude, and they are related by a small parameter. And although they can be treated asymptotically as different scales, in fact, they are not independent. They sort of talk to each other, and there is some locking phenomenon going on. Okay? This is, I think, an important literature on the subject. I'd like to point that we used a technique based on optimal truncation, and the first work I know of which used this technique on a multiple scale problem is that by Adam King and Tew on shockwave solutions of the Kuramoto-Sivashinsky equation. Earlier than that, there were already some work done by Yang and Aquilas and others. It's a different technique, but it also treats multiple scale problem beyond all orders. And I will return to the work of these 3 people later on. Okay, so what I'm going to show you is that there is a locking between these 2 scales. And basically, if you look at the speed of the wave packet, which will be a soliton, in the vicinity of the crossing between the group and phase velocity, well, the soliton will actually not go at the group velocity, but it will have an average velocity that follows this line here, and that will be locked to the phase velocity. And the other surprise is that, in fact, the motion is not steady anymore in this locking range. Okay? So in the locking range, you have actually an oscillatory motion with an average velocity that is given by the phase velocity. And if you go outside the locking range, you still have small oscillations, but you eventually tend to the classical group velocity. Okay? And this region here is exponentially small in this small epsilon that I showed you before. So this is the plan of what I'm going to say next. First, I want to introduce you a general wave model that already encompass quite a few physical situations, and to develop the multiple scale framework for that wave equation. Then I will sketch how to go to the leading and late terms of this multiple scale analysis, and we will find what lies beyond all that. And then we will go to the result of the discussion. And if you want all the details, this is now an archive. Right. So here is the wave equation I'm going to consider. It's not the usual way you would write it, but it has the advantage of making the dispersion relation directly appear in the equation. So E hat is the Fourier transform of the field that you are interested in, and then you have, beta is the wave number. If you just look at this term here and you make the Fourier transform here, you can easily guess that it's a superposition of Helmholtz equation in 1D. And this nonlinear term is typical of nonlinear fibers. It's what you get in the case of a Kerr nonlinearity. And so this is inspired from fiber optics, but you can derive such an equation in cold plasmas or elastic beam waves. And I will use my unit such that, well, the working frequency is, it's normalized to 1. The wave number at this frequency is 1. And also beta prime, which gives you the group velocity, is also 1, because this is that particular frequency around which I'm going to work. I'm sorry?
Beta is real?
It's real.
So basically you neglect Kramer's Kroning, just assume you some transparency window, right? Because generally beta must be complex, except you're doing some approximation.
Well, as long as attenuation is negligible, beta is real. Okay? So this is really standard in fiber optics. Okay? But yes, it's real.
It's approximation. I mean, it's not full.
Yes, it's always an approximation. Definitely. Yeah. So this is, as it were, this is a Hamiltonian system. It's a dissipationless system. Okay? Right. With this equation, as I said, so to see it clear, if you have, monochromatic wave, and if you set the nonlinearity to 0, then you recognize, Helmholtz equation. As for the dispersive term, is concerned, then if you have the spectrum that is strongly localized near a given frequency, then you can tailor expand the beta square that is here around omega, and this integral operator can be turned into a differential operator in this way, which applies directly to the slow amplitude that is given by this factor here. And that will be useful to apply a multiple scale analysis in the original equation that is over there. So here is the sketch of the multiple scale analysis. To lead in order, I will have the following ansatz. So fast oscillation, a slow amplitude that depends on 2 scales. This scale is attached to the frame moving at the phase or the group velocity. They are exponentially close here, so it doesn't matter which one it is. And capital X is a slow propagation scale that can also be seen as time after long propagation. And here I'd like to highlight X0. This is where the center of your wave packet here is, Okay? So if you assume these scales, which are typical, and you differentiate twice your field with respect to X, for this term here, you get a range of terms of ascending powers in epsilons and involving various derivatives of xi and capital X. And if you do look now at the dispersive term, then because the amplitude is slowly varying, here you have, the amplitude here is there, and the derivative with respect to time yields this term here. And you can expand this you can tailor expand this near the value of 1, and this gives you this contribution here. At this point, I need to introduce this coefficient. This is simply the coefficient of Taylor expansion of the function beta square around m times the fundamental frequency at nth order. So here, lambda nm is this guy here, and here you have lambda n1 because we are working near the fundamental frequency. So this is rather simple, and if you put all this into the wave equation and neglect corrections, then at the fundamental harmonic you have these various terms. The order 1 terms, they cancel immediately because by definition of the dispersion relation, beta 1 is such that it's equal to 1. Then if you look at this coefficient of Taylor expansion, it also gives you 0 here. At order epsilon, it compensates for that one. And all what is left is at order epsilon square. So I think I forgot to tell you, epsilon is both the separation of scale between the slow and fast scale. It's also defined such that epsilon square is the nonlinearity in your problem. Okay, so if you just look at what is left at the fundamental harmonics, it's basically the Schrodinger equation. I think this is familiar to you here. And there are obviously third harmonic terms that have not been cancelled and which you have to attend by adding extra harmonics in your expansion. Right, at this stage, I need to say a few words about the nonlinear Schrodinger equation. I'm going to focus on the bright soliton solution, which exists for that sign of the nonlinearity. It exists for a negative value of beta 2. Beta 2 is the second order chromatic dispersion. And this is the solution. It's well known. It's nothing new. And here what you have, in fact, this bright soliton is only one out of the family of solution. John has already actually shown you what this family is. You can write this family of solution in this way, and you can change the moving frame coordinate into another one where you have a cx here, and c is a relative velocity in the moving frame. And so if you let the soliton move at a slightly offset velocity c, this is allowed provided that you add this extra modulation here. And this extra modulation, in fact, physically, it means that you change slightly the frequency of your carrier wave so that everything is compatible with the expression for the group, the classical formula for the group velocity. Okay? So with this phase factor, the classical formula for the group velocity remains valid, and this is why this formula remains always, almost always true. Now suppose you want to have an accelerating soliton. So suppose that c is now a function of time or of x, the big X, which is the propagation variable. If you do that, and if you assume that the acceleration is small, then you can linearize nonlinear Schrodinger equation, and you get this extra correction here that's proportional to the acceleration, and you have this term Ra, which has the annoying quality to grow exponentially away from the center of the soliton in the moving frame. And that's obviously physically not allowed, and on the basis of that, we know that from textbook, a soliton is not supposed to accelerate. It moves at a constant speed, and it is the group velocity. However, the term that I've shown here is only the first of an infinite series which diverge, which has to be truncated. And if you look at the remainder of this series after truncation, if you truncate it optimally, then this remainder will contain terms that also increase exponentially away from the core of the soliton. And since it's there, we will actually need this other accelerating term to compensate for this exponential here. And that will lead to an equation of motion, a new equation of motion for the soliton. So, we have to compute the late terms of this asymptotic series. Let me describe you the various terms here. At order epsilon L, you have an increasing numbers of harmonics with amplitude which I call ALM. And one interesting thing is that if you have a cubic nonlinearity, the usual one in optics, it's a Kerr nonlinearity, then you usually only have odd harmonics. But if for some reason you have a quadratic nonlinearity, this also happens in nonlinear optics and in hydrodynamics as well, then the quadratic nonlinearity would yield harmonics of all orders which are both odd and even. Okay? But I will focus here on the cubic for the technical aspects and come back to the quadratic situation later on. So when we look at the leading order term, there's one important thing to know, is that the exponential decay of the hyperbolic second produces a strings of singularities in the complex plane of the moving frame variable. And in the vicinity of the closest singularity here, you have this pole here. And this, because of this, when you go to higher order terms, you will find this singularity again, but with a higher strength. I'll explain you why we will have this kind of expression for the high order harmonics at high order of the calculation. But what's important to see is that what we're going to have is a factorial growth of the term with L, the order of calculation, a stronger and stronger singularity, and then there is this factor here, I over kappa exponent to the L power. You will see why later. If you believe this, which is true in the limit of large L and where I can neglect 1 over L terms, if you believe this, then you can use Dingel's rule for beyond all order asymptotics to immediately locate Stokes lines. And according to Dingel, you will have Stokes lines where successive terms in the series have the same phase. Now, if here kappa is a positive number, then you will have the Stokes line that will go down from this singularity here. If kappa is negative, by looking at this here and just looking at the phase of successive term, you will realize that when kappa here is negative, you have a Stokes line going up from that singularity here. Okay? Right. So how do I know that I have such an ansatz, or such a behavior for the late terms of the asymptotics? Well, let me plug that into the equation. So if I just use this in my series, I have various terms for that particular harmonics, and if I differentiate it twice with respect to x, well, I will have, when I differentiate this guy twice with respect to x, I will get a minus m squared term. Here, when I differentiate twice, I have one differentiation with respect to x and two differentiation with respect to psi, and that will produce me an extra factor L, which will combine with the gamma function to give me something of the same order as the other terms. And that gives me that term here. And if I look at L minus 2 here, when I differentiate it twice with respect to the variable psi, this gives me this factor here. So differentiating it twice gives me this nice factor here at order epsilon L for the mth harmonics. And you can do the same exercise with the dispersive operator. Now, we are playing around the mth harmonic, so if you just do it, you will now be faced with these Taylor expansion coefficient lambda nm, which are related to beta square around that frequency here. And if you just look at this closely and do it step by step, you will realize that one line after the other, you get to leading order in 1 over L, this simple expression here, beta square of m plus kappa. So these two terms, when you put them into the equation here, they will produce this expression at order epsilon L of the calculation. The nonlinear term here is present too, but it's smaller by a factor 1 over L square due to this factorial growth here. Now, if you look at this term here, you realize that the problem has been greatly simplified. And since beta square of 1 is equal to 1, in fact, you have a general solution that for the harmonic m, kappa is such that m plus kappa is equal to plus or minus 1. And so that means that each harmonic is associated to a certain value of kappa in this ansatz, and in such a way that it solves to leading order the linear part of the equation here. And because there is this 1 over kappa to the L term here, the smaller the kappa, the more dominant contribution you will have. So the most dominant contribution comes from kappa equals 2 and kappa equals minus 2, and they respectively correspond to m equals minus 3 and minus 1, and 1 and 3. I remind you that for the cubic nonlinearity, we only have odd harmonics, and this is why we have kappa equals 2 or minus 2. Okay? And if you are brave enough to continue the calculation and include order 1 over L term, order 1 over 1L square term, then you will find that you can find what is the value of this offset here. There are 4 possible values, and the largest one is equal to 4. And in that case, the 2 harmonics that are concerned, that are related to a given value of kappa, they have the same sign, and they're actually purely imaginary. So it's I times lambda k. Lambda k is some numerical constant that can only be found numerically. Okay, with that, what we find is that we can have the leading terms are for kappa equals 2 and kappa equals minus 2. And for the positive kappa, these terms here will produce a Stokes line in correspondence to the harmonics m equals minus 3 and 1. And for kappa equals minus 2, you will have a Stokes line emanating from this singularity, and that Stokes line will cross the real line for psi. Okay? And if I had used a quadratic nonlinearity, then I could have had kappa equals 1 or kappa equals minus 1, and in that case, the corresponding harmonic would be minus 2, 0, and 0, minus 2. And these are the values of kappa that would lead to the dominant contribution beyond all orders. So, near the singularity, we just found out that we had this general behavior. So the alpha is equal to 4. We have certain values of kappa. They have to be integer, and for each value of kappa, we have 2 harmonics which are associated in this way. And based on this, we can construct the solution away from the singularity in the following form. For convenience, I put L plus 4 here. It's going to simplify nicely with this gamma function. And I'm free to do that because I allow myself to have a general amplitude Fm here. So I can redo the same kind of thing. It's a bit technical, so it's in the archive. But at the end of the day, what you have for this amplitude Fm is a linearized equation from the NLS equation. So basically, Fm is one of the solution of the linearized nonlinear Schrodinger equation. And the one that matters is given by this. I don't spell it out. What you have to know is that this amplitude here is growing like e to the psi over this factor as psi becomes large and positive. Okay? And so this is part of the solution, and there is a similar contribution that comes from the mirror singularity below the real line. So now that we know that, we can truncate the system. And thanks to the factorial ansatz, we know that optimal truncation happens at some large order L given by kappa r over epsilon. So we know where to truncate. And if we do that, we can derive an equation for the remainder, which is a linearized version of the original wave equation. And it is forced by two terms, which I don't dare to show you. One comes from the top singularity, and one comes from the bottom singularity. And there are forcing terms that will drive the remainder equation, and that comes from the fact that this doesn't fully satisfy the wave equation. So near the Stokes lines, we introduce Stokes coordinates. So let's look at the top singularity. We know that the Stokes line goes down. So I write psi naught minus IR, and then I write epsilon to the 1/2 times s, so that's an horizontal coordinate. And so locally, I write a new coordinate in this way. This is the Stokes coordinate, but I could asymptotically, in an equivalent way, write psi naught minus psi is equal to this exponential there. So in the limit of small epsilon, this is asymptotically equivalent to this, and that's easy for calculations. So when I look at the late terms that make up the forcing term of the remainder, well, I'll get terms of the following form, which the factorial factor and one of the singularity that is here. And I can use Stirling formula to simplify this factorial in the limit of large L. And can put everything together in this way. There are some technical steps here which you can look later on if you look at the slides when you have time. At the end of the day, what a term like this, which appears in the forcing term of the remainder, looks like, it's something like this. So what you find is that you have the original harmonic oscillation, which is here. And this term here oscillates locally very fast near the Stokes line. And it produced this new term here that oscillates fast. If you combine this term here with that term here, you have e to the I k plus m times x minus t. So, but k plus m is equal to plus or minus 1. So that means that all of these terms, all of these harmonics, they become locally resonant with the fundamental harmonic. So they will drive it locally in a resonant way. The strength of this driving is very small. It's exponentially small here. And it happens in a way that will produce like a Stokes switching that is typical of Berry smoothing of Stokes discontinuity. Right, and in the process, what you find is that there is also this factor here, this x naught, which comes from the definition of the slow variable psi. It appears here, so it will become important later. So near the Stokes line, what we've got is that the harmonics associated to positive kappa yield a Stokes line from psi naught. It's of the following shape. And you have something symmetrical from the bottom singularity. And so if you combine all this, at the end of the day, it will produce downstream the soliton. It will produce a term that is like cosine of x minus t. And then there is this function here that grows exponentially with x, with a certain phase where you have x naught here, and a very small amplitude. And if you now combine this with the acceleration term, you put them together, then you find that beyond all order, you have this extra contribution to the soliton solution that is of the following form. And since this is growing exponentially, this is unacceptable, and we have to put these terms between bracket equal to 0, and this is the equation of motion of your soliton. So C, as I said, it's a velocity in the moving frame, so it's basically proportional to dx0 or by dt, and d by d capital X is a propagation coordinate, so it's also proportional to t. And so basically here you have an acceleration term here that is proportional to d to x0 by dt squared. So what is the equation that you get at the end of the day? It's a pendulum equation. Okay. So I've kept the kappa, as you can see, because now I can treat both the cubic nonlinearity and the quadratic nonlinearity into a same equation. If the nonlinearity was cubic, kappa would be equal to 2, and if it's quadratic, it's equal to 1. Here, eta is plus or minus 1. It's basically the sign of this numerical constant. You have to find it out numerically. And then you have this so-called locking velocity, which is exponentially small and related to our scaling in this way. So what do we get? The pendulum equation, we know how to solve it. And here is the phase portrait. Here is the speed in the moving frame. And here is the position of the wave packet in the moving frame. And you see that if you are in this region here, then you are in the locking range. And you make circle motion around a steady point, so you are still moving at the phase velocity. And here you are outside the locking range. In the locking range, you have two steady points, one here and one there. This one is unstable. And here I show you how does it look like for the stable in black and the unstable in red solution if you have a cubic nonlinearity and eta equals 1. And if you had a quadratic nonlinearity, then depending on the sign of eta, then you would have, for instance, a trough in the middle or a crest in the middle as the two possible steady-state solutions, and only one of them would be stable. And moreover, for the unstable one, you can find the growth rate of the instability as you go along the separatrix. It's very easy to do by linearizing this thing, and the growth rate is basically given by this exponential here. So it's an exponentially small growth rate. And what's nice is that, as I mentioned, there was a work by Calvo, Yang, and Aquilas, and they were looking at a different equation. They were looking at the fifth-order KdV equation, which was an excuse to study gravity capillary waves. And they were looking at stationary profile that exactly move at the phase velocity. So they were basically looking at these 2 points here and there. And thanks to the input of Calvo, they could find out that only these two existed. So the phase of the oscillation was not free, and which is the same as here, and also that only one of them is stable, which is the same as here, and they got even a scaling for the instability rate of the unstable solution that agrees with this scaling. So that's as far as I can get for numerical confirmation of these results. And importantly, KdV is a one-way wave equation, so it's not of the form that I have studied here. So it gives confidence that the kind of calculation I've done is universally valid. Okay? So let's go to the conclusion. So you don't have to throw away the nice formula for the group velocity. But if somebody tells you that it's always valid, you can always raise your finger and say, no, it's not always valid. There are some situations which it's not true. And for this not to be true, you need a certain number of things to happen. It must be a multiple scale situation. You have separation of scale, but that's not enough. You need nonlinearity, because in the details of the calculation I've shown, it was crucial to have this interaction with higher harmonics of the fundamental. Okay. Another way to see that is that it is the nonlinearity that provides this hyperbolic second solution with exponential tail that produces singularities, these strings of singularities in the complex plane. And these are, as you have seen, important to produce these beyond all order terms. Also, the nonlinearity allows you to have a soliton, something that moves for a long distance without changing shape, and so that the ratio between the slow and the fast scale remains constant for a long period. It needs to be so in order for the exponentially small term to have an effect on the dynamics of your soliton. Okay, that's pretty much what I wanted to say, but I also want to mention that there are other perspectives about this. The equation for the soliton is that of a pendulum subjected to a periodic harmonic, a periodic potential, basically. So there is like a periodic potential for force sensed by the amplitude of the wave packet. And now if you have two wave packets interacting together, they have a textbook interaction through their tail, but you have to consider the possibility that now there is also an extra interaction that is periodic between two distant wave packets. So the interaction between two wave packets can also be modified from the textbook reference due to this beyond all order effect. And I would like to conclude this talk by saying that this work needs badly numerical confirmation beyond that of Calvo and Yang and Aquilas, but it's extremely challenging to simulate these effects numerically, because you cannot simulate the NLS, you have to simulate the full wave problem, including the small and fast scale, and you have to simulate it very precisely, very accurately for a very long time, since the exponentially small terms are exponentially weak. So if anybody is interested, I failed, but that would be a very nice result if somebody could be able to do such numerical confirmation. Thank you for your attention.
So just to get some idea, so you have with multiple harmonics, right, in this theory, but for some, if check your theory, what you mentioned in simulation, do you have any clue how many harmonics would be necessary to take into account to get your effect? Is that hundreds, thousands? I don't know.
Well,
I understand it's a difficult question depending on initial condition, but still some clue.
You mean from a theoretical or numerical perspective?
Both.
Okay. From a theoretical perspective, what I really need is the first harmonics. So, because these are the ones that will primarily interact with the fundamental ones. So, if you remember, there was this kappa equals 2, and this was associated to the harmonics 1 or -1 and -3. And if you have kappa equals -2, it's harmonics 1 and 3. So these are the ones that yield the dominant exponentially small contribution. So it would be enough to have these ones. So on the other hand, if you want to do accurate numerical simulations, well, I don't know. I don't know. It's already hard enough to precisely simulate. Definitely, you have to have these ones, but you will see you precisely need to simulate these harmonics and the small details, the slow motion about this.
But do you mean that if you just truncate to with couple harmonics or whatever, 5 harmonics with high precision, we will get all your effects? Because my impression was that it's also effects sit on higher harmonics, but maybe I misunderstood.
Yeah.
So when it will be
no,
not,
but you're right. You're right. Your question actually, I think you understood it better than I do. Yeah, it's true. As I explained, in order to go to high order, when the further you go to higher order, the more harmonics you have, and you have to go to high order, so you need to catch these harmonics. I don't know if numerically you need to go to the 10th or the 15th harmonics, but at least theoretically, yes, you need to take into account these many harmonics. They will arise in any case.
Yeah, I think numerically it's doable, but last comment which I mentioned, it relates to comment very beginning. If you're looking for some practical application to optical fibers, if you're going to really high harmonics, eventually you go out of transparency window and you have to take into account dissipation. But I mean, this is if applied to some experimental application. Of course, if mathematical problem, you have well-posed problem. Yeah. Thank you.
Any other questions?
Are you sure you can't reduce it to a OD in a moving frame? The reason I ask is that King and I looked at a problem once where you could think of it either as a smooth solution that was jittering as it moved, or you could think of it as a jittery solution that moves smoothly. If you see what I mean. So if you wrote it as a traveling wave, but then the asymptotics of the solution may be different because the multiple scales oscillation would be built into the profile now. It's a different problem, so I'm not sure, but it's
a different problem. I think it was a discrete differential problem. Yes. In your case, the discreteness provides for the multiple scales in a sense, but I didn't find any inconsistencies that led me to think that that was not correct. So far, everything I did seemed consistent. And I didn't find the necessity to. No,
But so for us, you could look at it either way. So you could introduce a sort of modulated space, I guess, but you already, I'll think about it.
But I think that in your case you had this staircase, which is the fast bit, and the fast bit that I have here is the carrier wave. So I think the two ingredients are there. You had these two ingredients in your work. And they are built in from the beginning in this physical problem.
Yeah, maybe that your fundamental is causing issues. Okay.
So thank you, Gregory, for highlighting some challenges for us to talk about later today and during the week as well. Let's thank him again. And then we'll have lunch at Churchill College, and the next talk will be at 2 p.m.